Okay, so we've solved for the wave function for the infinite potential well. Well, now we want to practice with it, and we're going to use some of the things that we learned in the previous chapter. So here we go. So we're going to concern ourselves with the n equals 2 state for no good reason, and we want to find the probability of finding the particle in an interval of 0.01 L at x equals 0.25 L. So again, this is a tiny, tiny interval, you know? So we're going to use that formula that we learned last time. Here's the formula. Right? So here's x equals 0.25 L. So we want to find the probability that whatever particle we're talking about lands in that tiny little width, right? 0.01 L. So here it is. The probability that the particle lands in this width, delta x, at x, equals the probability density, probability per length times the length, which is psi squared times the length. Now psi squared, well that's psi, so this is psi squared, right? So psi squared times dx. Okay, so that's not bad. All right, so let's do it. So what we want the probability that the particle lands in 0.01 L at x equals 0.25 L. And that equals, it's just the P2 state, right? So it's P2 at 0.25 L times our delta L, right? Times our delta L, which is 0.01 L. All right, so that's what we have to do. So that, okay, so this, that's just the psi squared, right? So that's psi 2 at 0.025 L. Oops, 0.25, sorry. 0.25 L squared times 0.01 L. Okay, we can do that. So just put in psi 2. So psi 2, okay, so this is psi 2 squared, right? This is psi 2 squared. So we're just going to plug it in. So 2 over L sine squared. Okay, n is 2, right? N is 2. This is the n equals 2 state. So n is 2, so 2. And then pi. Then x, and x is 0.25 L. So 0.25 L. Then the bottom is L. Okay, so there's that. So there's this part, right? That's that. And then times our width, which is 0.01 L. Okay, now we've got to evaluate that, right? Okay, so let's see. So that L kills this L. 0.25 is a 4 on the bottom, right? And a 2 there and a 4 there becomes a 2 here. Okay? So let me just rewrite it so you can read it. So 2 over L sine squared pi over 2 times 0.01 L. Okay. What is the sine of pi over 2? So what's the sine of 90? It's 1, our favorite number. Well, second favorite number. Favorite number is 0. Okay, so sine squared of pi over 2 is just 1. So that's nice, right? Just have a 1. And then we have a 2 over L times 1 times 0.01 L. So what happens to the L's? Goodbye, right? And then all we get is 2 times 0.01, which is 0.02. So that's the probability. And if you want to, you can say that's 2%. Okay? So that's how you do it. So that's using this equation from last time. We have a really, really narrow interval. So now let's do another one. Okay, so this is the one where we do a small one. Let's do one that we have to do a large interval, because that was the second type of problem we learned last chapter. So let's do that. Let's see what I can find. Okay. All right. So same, n equals 2, right? N equals 2. What's the probability of finding the particle in the first quarter of the box? So, all right, so now we want the first quarter, right? So what's the probability of finding it between here and here? Well, come on. What's the answer? I mean, this is the same as this, which is the same as this, which is the same as that, right? So the answer is 25%. But that's not good enough. You got to work it out, right? Because I'm not going to give you something easy like that on a test, right? So let's work it out. All I'm saying is, you know, if you have an opportunity to check your answer, you should do it. All right, so what's the probability of finding it in the first quarter? So now we want the probability that the particle is in 0, I'm just going to be lazy, 0 to L over 4, right? I could have said, you know, 0 greater than equal to x, greater than less than equal to L over 4, or whatever. Okay, so that equals, okay, what's the probability? It's 0 to L over 4 times probability density. P2 of x dx. Again, this is probability per length. That's the length, so we get probability. Okay, so we got to square the thing again. No problem. So we have, and this is on the outside because it's just a constant, so we have 2 over L, integral 0 to L over 4. That thing squared. Sine squared. And remember, n is 2. So we have 2 pi x over L dx. Well, again, we say, sine squared, right? I mean, if you can integrate that, great, but I have to look at tables. So we have to look at the integral tables again. Okay. And now what's our a? Now our a, you know, this a, now our a is 2 pi over L. So let's do it. So we have 2 over L. Okay, x over 2 minus, now we're going to flip this thing, right? Because that's 1 over a. So we flip it, and we get an L over 2 pi. But then we have to divide by 4, so we get an 8 pi. So we have L over 8 pi sine 2ax. So 2 times 2 is 4, so it's going to be 4 pi. So 4 pi x over L. Okay? And then we're going from 0 to L over 4. Oh man, I need some room. Okay, so now we're back up here, right? All right, so we have 2 over L. Put in our x. So our x is L over 4, but then we're going to divide by 2. So we get L over 8. Then minus L over 8 pi sine. Let's put the L over 4 in. So we're going to have an L over 4. So the L's kill, the 4's kill. I get sine of pi. Sine of pi is 0. Yes. Okay. So that don't have to worry about that, right? Or minus, who cares, right? And then, all right, so now we're done with him. Now we go to this one, 0. So that 0 over 2 is 0. Sine of, this was an x in here. Sine of 0 is 0, so that goes away. So we just get another 0 or minus 0, whatever. Anyway, we just get all zeros. So the answer is that. And then L's killed. 2 over 4 is a 4. 2 over 8 is a fourth. So 25%, which is exactly what we expected. So it's just nice that it works, you know. So anyway, make sure you can do those problems, because that's what you're going to see on your exam and your homework from last chapter as well as this chapter. So it must be important. Okay, so this is our, what I call the Randy Knight problem-solving strategy for these quantum mechanics examples. First, we want to determine a potential energy function that describes the particle's interactions. And we want to make simplifying assumptions. Okay, and if we want to, we can visualize the potential energy curve, right? Okay, so if you want to, draw the potential energy curve, identify everything you know, and you have to establish boundary conditions that the wave function must satisfy. You have to do that. Okay, the Schrodinger equation is like the mathematical representation. So utilize the boundary conditions, normalize the wave function. If you want to, you can draw graphs of psi and psi squared. This, of course, gives you the indications of the probability density. Determine the allowed energy values, calculate whatever you want to calculate. And don't forget to assess, right? Make sure everything you've done is reasonable. Correct units, answers are reasonable, answers the question. All right. Okay, so that was our first example. That was the infinite potential well. Now let's do something more realistic. Let's do a finite potential well. But before we do that, we should review physics 121. So let me do that. Okay, so here we have a finite potential well. In other words, the potential, it just goes up to here, right? It doesn't go up to infinity. This is the potential energy. And I have no idea this is just some crazy thing that somebody thought of, right? I'm not saying it represents anything physical. So it's a finite potential well. So again, physics 121. So the red line is the total energy, 1.5 joules. A particle with mechanical energy 1.5 joules is moving to the left. Just as it passes x equals 2, it's hit from behind and by a moving marble. The collision increases the particle's energy by 1 joule. So now you're at 2.5. What happens to the particle? Well, it's going to keep going to the left. Then it's going to hit this where the kinetic energy is 0. Then it's going to bounce, reflect, and go here. And here, since total energy is greater than the potential energy, which means it has kinetic energy, it's just going to keep going. So that's something that's important. So remember on these situations, the energy equals U plus K. So here, the U equals the total energy, right? So the energy is 0. So it stops, and then it turns around. Now here, this is the total energy, U plus K. This is the potential energy, U. So U plus K equals that total energy. So when it's right here, it can just keep going, right? All right. So that's physics 121, which we all know and love. Now let's do a different. This is still physics 121. Okay, kind of messy, sorry. A particle at 3 meters, right here, has 0.7 joules approximately, I don't know. Okay, it's moving to the right, doesn't really matter. What happens when it reaches the position shown? So it's right here, right, and it hits there, or it could hit here, I don't really care. So when it hits here, again, energy is U plus K. When it gets to this point, which is a turning point, so you know the answer already, when it gets to that point, the U equals the E. So that means K is 0. So what does it do? It stops and it turns around. Then it goes over here. It's supposed to be right here. When it gets to here, the K is 0. So it stops and it turns around. So what's it going to do? It's stuck. Remember, we talk about stable equilibrium. So it's just stuck. So it just oscillates, it just oscillates. So that's according to classical physics. And we discussed that in gory detail in physics 121. Ha! Well, now we're going to see what really happens in the quantum world, right? In the quantum world. So what we want to do is we're going to look at a realistic problem. So this is a semiconductor. Don't worry about that. It's just something that sometimes acts like a conductor, sometimes it doesn't. And there's an electron located in a really narrow well, 2 nanometers wide, right? 2 nanometers wide. And it's not very deep. It's only 1 electron volt deep. Okay? So, realistic, okay? An electron in a 1 eV, and it's finite, agree? It doesn't go to infinity, It's only 1 eV deep. All right. So we're not going to, well, yeah, we are. But first I'm going to just show you the wave function. And then we'll do the math. Don't worry. So here's what happens. And again, this is one of these pictures where there's two things being shown. The wave functions are being plotted along with the energy. Okay? So look. Well, by the way, back off. Back up. When we had the infinite well, how many different solutions did we have? Well, infinity, agree? Just infinite solutions. Now we have a finite potential well. How many solutions do we have? 4. That's all you have. 4 solutions. Okay? With bound states. Now, let's start off by talking just about the n equals 1 state. All right, so here's the n equals 1 state. Yeah. What's the energy of the n equals 1 state? Well, you can see right there, right? 0.068 electron volts. Okay, how does this compare with the depth of the well? Well, the well is 1 electron volt. This is only 0.068, like 0.07. So this is much, much less, right? It's like me, being in a building with I don't know, with walls, way up there, right? Classically, I can't escape that, right? But wait a second. Look at the wave function. The wave function, doesn't stop here like it did with the infinite well. It goes outside the well. What? Yeah, the wave function goes outside the well. Now, what does that mean? Well, remember, the probability density is the wave function squared. So if the wave function extends outside the well, that means it's probable, right? There's a non-zero probability that the particle exists outside the well. Wait a second. That's insane. Right? I mean, how can that be? E equals U plus K. Right? Right here, E is 0.068 eV. U is 1 eV. What does that mean that K is? Well, it has to be negative. What? What's negative kinetic energy? Well, okay, classically it would be negative, but this is not classical physics, all right? So all I'm saying is, this is totally ridiculous. This is totally impossible according to classical physics. But in the real world, in quantum mechanics, when you're describing tiny little things, it's true. It's real, okay? You can extend past this classical forbidden area, okay? Wow, that's weird. Welcome to quantum mechanics. All right, so we have classical impossibility. Now you think, look, you think that's bad. Yeah, just to remind you, this is the infinite well. See how the wave function just stopped right there? Bing, bing, right? Because the probability that the wave function couldn't extend because it's impossible. But again, in the real world, look at this one just extends a little bit. Look at this one. Look at this one. Look at that one. So in quantum mechanics, it's okay. All right, it's okay. Now, this is going to be tough. So you really want to pay attention, okay, what we're going to do now. So what we want to do, okay, we want to investigate this. We want to investigate what's happening over here in the classically forbidden area. Because that's the fun part, right? Okay, so, boy. Okay, so this is kind of too much stuff on this drawing. So here's the well. Okay, here's the well. Here's the energy E. Here's the 1 eV height, right? This is the classically forbidden region, right? So it says X is greater than L, right? So see here, we're saying that this is L now, right? The length, 2 nanometers. So this is L. Right? We're just looking at that. Okay, all right? So we're just looking at the X greater or equal to L region, the classically forbidden region, because that's where it's fun. All right, here we go. All right, so just over that region. Okay, here's the Schrodinger equation. D squared psi dx squared equals minus 2m h bar squared, oops, minus 2m over h bar squared. And then E minus U psi. Okay, so that's the same thing as the Schrodinger equation. I want to get this separated. You'll see why. There's a good reason for it. Okay, now notice over here, U is bigger than E, right? So if U is bigger than E, what's the sign of E minus U? It's negative, which is impossible classically, but who cares about that? We're doing quantum mechanics, right? Okay, so this is less than 0. But we have a minus sign here and a minus sign here. Psh, goodbye. So let's get rid of all those stupid minus signs. Why did I have a 0? I don't know. Not supposed to be a 0 there. Gosh. All right. So minus minus. So we're going to just say 2m over h bar squared. And we're going to say u minus e psi. All right. Now, u minus e. So u. Okay, u minus e is positive. Okay, let's put a little u0 to make it agree with that picture, whatever. Okay, so, and now we're going to do a trick that you've seen me do before, and there's a reason for it, so just don't worry about it. What we're going to say is, we're going to say that this, we're going to say that that whole thing is equal to, okay, we're going to say that 1 over eta squared, this is eta, not an n, 1 over eta squared equals 2m over h bar squared u0 minus e. And we're not just doing it because we're lazy, although that's not a bad idea, you know. I mean, it's going to make it look nicer, but there's a reason for it, and you'll see why later, okay? So now what we have is just d squared psi dx squared. Okay, we lump all this as 1 over eta squared, 1 over eta squared psi. Yeah, all right? Yeah. Okay? All right. Now, let's just do a little thinking before we do the math. Here we have a psi. Here we have an x squared. So we have a psi over a length squared. Here we have a psi over eta squared. So what does eta have to be? It has to be a length. So eta has to be a length. And we'll see soon enough that that's a really important length. Okay? You remember when we did this with the infinite well, we had a beta squared, you know, and then we showed that energy was quantized. So we learned a lot. Well, we're going to learn a lot from this eta. It's eta, not an n. Golly. Okay. All right. So here you go. D squared psi dx equals 1 over eta squared psi x. And eta is positive. Now, when we did the infinite potential well, we had a minus sign. So we had the solution were sines and cosines. Well, now, what are you going to do? Now you have a function. You differentiate it twice. You get the same thing back with a coefficient, but positive. So sines and cosines aren't going to work. So now you've got to think a bit, all right? So think a bit. So yeah, pause your video, students, and think a bit. So just come up, you know, think of all the functions you've learned, that if you differentiate them twice, you get the same thing back with a positive. Okay, I hope you've figured it out. So the only thing that will work is just the exponentials, right? The exponentials. So, you know, e plus or minus ax, right? If you have e to the ax, you differentiate it twice. You differentiate it once, you get a e to the ax. Differentiate it twice, you get a squared e to the ax, right? So you get the same function multiplied by a coefficient. If you have e to the minus ax, You differentiate it once, you get minus a e to the minus ax. Differentiate it twice, you get minus a times minus a e to the minus ax. So in other words, you get a squared e to the minus ax. So you get the same function as you started with, multiplied by a positive coefficient. So that's going to work, all right? But again, you know, you have to have two independent solutions. So I'm going to erase. All right, so we get erased. Okay, so we know that the answer then, before we do our boundary conditions and all that stuff, a e to the ax, or wait a second, sorry. We have eta on the bottom, so we get to divide, right? So a e to the x over eta plus b e to the minus x over eta, right? The x, remember, the eta was on the bottom, so we got to have it on the bottom. All right, so we have two independent solutions just like what we wanted. So that's wonderful. Now we got to do our boundary conditions. Okay, so let's just kind of be smart about this. So we know that the wave function at infinity is 0, right? That was one of the boundary conditions. Well, if you put an infinity up here, okay, what's e to the minus infinity? That's 0, so this is fine. But what's e to the positive infinity? Well, some gigantic infinity number, right? So a has to be 0, right? For this to work, a has to be 0. So therefore, a equals 0. Oh, that's good. Okay, now, that's cool. Now we want it continuous at x equals L, right? That's what we're dealing with, right? So let's do that. Well, not yet, I guess. Okay, so we're going to say, all right, so a is 0, goodbye. So we're going to say psi at L equals b e minus L over eta, right? Okay, now, this is the wavelength right here, right at this edge, you know? So since it's the wavelength at the edge, we might as well call it wavelength at the edge. Okay, so the wavelength right here, we can call psi edge. Okay, so this is psi edge. Just a nice name, you know, psi edge. All right, well, if that's true, then what's b? Well, therefore, b is equal to psi edge divided by this thing, divided by e to the minus L over eta. Well, and that's, of course, the same thing as psi edge e to the positive L over eta. Right. Okay, so we've just figured out our b. Yeah? So b is psi edge e to the L over eta. So therefore, okay, so now we know our b, right? Now we know our b. So therefore, psi of x equals a b psi edge e to the L over eta times e to the minus x over eta. Okay, now you're not going to write something like that, right? Because you have two, I mean, you know, might as well multiply it together. So we're going to get psi edge. Now what do you do for exponents? You add, right? You add. So we're going to get e to the L over eta, well, L minus x over eta, right? I mean, right? So L minus x over eta. I don't like it like that. You'll just see why in a minute. So I'm going to just do a little math trick, okay? I'm going to multiply the top by a minus sign, and I'm going to multiply by the bottom by a minus sign. That's totally legal. So then I have psi edge e to the negative L plus x over negative eta. And this is the same thing as x minus L, x minus L. And then I can put the minus sign wherever I feel like it, right? So I think I'll just put it up. Instead of putting it in here, it looks stupid down there, don't you think? Let's put it up here. All right. And there's a reason for that. You'll see. It's a minus. Okay? So there it is. Awesome. So we did it. So the wave function is, again, this is just, all we're concerned with is over here. Because that's where the non-classical work is going on, right? So the wave function, psi of x, equals psi edge e to the minus parentheses x minus L over eta. Awesome. Now, whoopee! Okay. Now okay, we know eta is some kind of a length, and we know it's supposed to be important, so let's really see what's so great about it, all right? So let's see what's so great about this eta. All right, so now we want to discover what's so phenomenal about eta. You know, what's the eta is a length. Well, what kind of length? What is it, you know? Okay, so what we want to do, here's x equals 0, x equals L. What we want to do, we want to look over here, and we want to put x equals L plus eta. So we're somewhere over here, right? Because we want to go over here. So we're just investigating to see what's going to happen. So we're going to put x equals L plus eta. So we're over here in the non-classical region. Okay, let's do it. All right. Okay, so now we're going to say that. Okay, we're also going to be a little bit lazy. All right? Well, no. So we're going to have, so this part is going to become, so we're going to have psi L plus eta equals psi edge E. Remember, x is L plus eta. So minus parentheses x, L plus eta, minus L divided by eta, right? That's what we have. Okay. Well, let's see. That equals psi edge. Now, L minus L is 0, right? Then we're going to have minus eta over eta. We have minus eta over eta. That's just negative 1, right? So that's just going to be psi edge e to negative 1. Okay. Well, what's that? Well, okay, people that do math, you know, they know, everybody knows e to the minus 1 is 0.37. So this is equal to this is equal to 0.37 psi edge, right? E to the minus 1 is 0.37. To put it in your calculator, if you don't believe me. All right? Okay, so what does this mean? What does this mean? It means when the wave function penetrates past this x equals L, you know, into the classical region by a distance eta, the amplitude of the wave function decreases to 0.37. Yeah? That's what it means, okay? So the wave function, right? This is psi edge. When it goes eta over here, whatever eta is, right? Here's psi edge. When it goes eta over here, it becomes 0.37 as much, all right? So the amplitude goes to 0.37, okay? That's what it really means. All right, so, man, what are we going to call this eta? We've got to give it a name. So eta, we're going to call the penetration depth. Penetration depth. Because if you look at eta past the edge, the psi goes to 0.37 psi edge. Okay, that's what we're to say. All right? Oh, I don't know, That's kind of cool, I think. So there, this is what I'm talking about. All right. So here is this crazy wave function. Here's the L. So this is classically forbidden. We're into the classically forbidden. We go, this is eta, right? Because here's L. Here's eta. And what do you notice? Here's psi edge. And then when you go eta into it, into the classical region, the wave function is 0.37 psi edge. That's all. And what would it be if you went 2? It would be, probably e to the minus 2 or something like that. So it's just mathematically simple, Because then you can go, e to the minus 1, e to the minus 2, e to the minus 3. And we saw that in other classes. We saw especially in Physics 220. Okay, so let's do some examples. Okay, just for fun, let's look at the n equals 3 state. N equals 3 state. Now, you can use this formula. You know the U, you know the E, right? You know the U is 1 electron volt. You know the energy is 0.585. So you can plug the numbers in here, the mass of the electron, h bar. You can plug all this junk in here and solve for eta. And I did that. So for n equals 3, you put all the numbers in here, and you get eta is 0.3 nanometers. All right? Okay. Now, look at the width is 2 nanometers, right? This width is 2 nanometers. So for n equals 3, this eta, 0.3 nanometers, it's 15%. All right? This here, if this is however eta is, it's 15%. So the eta is 15% of that. Whatever eta is, I don't know. It's 15% of that. And that's easily measurable. It's easily measurable, all right? And so the electron really, really does go past this classically forbidden region, okay? Let's go to this guy. This guy is way outside, right? So for n equals 4, eta is 0.86 nanometers. Again, you just calculate that from this, because you know the energy and you know the total energy. 0.86 is 43%, right? So here's your 2 nanometers, this, and eta goes to almost half as much. It sticks way out there, okay? So anyway. All right, and again, that's super easily measurable, and people measure it. And if this didn't work, you wouldn't have, transistors, you wouldn't have cell phones, you wouldn't have modern electronics, you wouldn't have all sorts of things. So this is real. All right, just a couple of review questions first, and then we'll quit. All right, this is a wave function for a particle in a finite well. And it's finite because it doesn't just go to 0, right? It has this like that, right? It doesn't just go to 0 like the infinite well. So finite well. What's the quantum number? This is a total piece of cake, I hope you understand. So pause your videos and figure it out. Okay. Right? How do you know that? 1, 2, 3, 4. That's how you know it. Okay, remember we saw that? Let me refresh your memory. Come on. Remember? So this was like n equals 1 hump. This was n equals 2. Well, let's go to this. N equals 2 humps. N equals 3 humps. Same thing here, right? N equals 4, 1, 2, 3, 4. So that's nice. Okay. All right, how about this? So you pause your video and figure it out, please. Okay, a rigid box, n equals 3. So n equals 3 humps, right? But then you want psi squared, so you flip them, so you get 1, 2, 3 humps. And then we want, where's it going to be, where's the highest probability? Right here, and right here. So 1/6, 3/6, 5/6. Okay? All right. Okay, one more thing. All right. Classical physics works for large, slow things. Now, what's large? Bigger than an atom. What's slow? Much less than the speed of light. Okay? But classical physics does not work for things traveling at nearly the speed of light, and it doesn't work for things, atoms, and smaller. Okay? Quantum mechanics works for everything. Now you have to use relativistic quantum mechanics if you want, relativistic things, but let's just say slow things, right? Quantum mechanics works for big things and for small things. But you'd have to be crazy to use quantum mechanics for large things because it's just way too much work. And why should you? Classical physics, which is easier, it works, okay? Well, how about things kind of like in between, So this is kind of addresses that question. What do you do for things kind of in between, Not really small, not really big. So this is the Bohr's correspondence principle. The average behavior of a quantum system becomes like a classical system as n, n, psi n, we have all these n's everywhere. Well, wherever. We had n's. Remember we had an n up here, and we had an n pi x for our sine and all that. The average behavior of a quantum system behaves like a classical system as n goes to infinity, where n equals a quantum number. Okay? So there you go. Okay, let's quit.